Okay. So we started talking about nonlinear dimensionality reduction. Uh, so linear, we know PCA, we know this Johnson-Lindy-Strauss lemma with random matrices. We know some other tricks here and there. Now we are trying to use nonlinear techniques to reduce dimension of the data if we want to. Let me just recap some of what we talked about last time. So this is called metric MDS, metric multi-dimensional scaling. So what is it? What does it do? You can do whatever you want, linear, nonlinear, to transform your data xi to some zi. Okay. Suppose this is like a small latent space. Think about it that way. And then at the end, your goal is to keep the distances between your data points not change so much. That's called metric scaling, metric MDS. So if you would do this linear, it will be similar to, for example, Johnson-Lindy-Strauss lemma does something like this in a linear way. And the threshold is like we can go up to log n dimensions, roughly speaking, if you have n data points. But sometimes you just want to go for 2, 3 dimensions to visualize. That kind of stuff cannot do it for you. Okay. So you allow yourself to use whatever neural net or whatever you want, nonlinear. This will be your loss function. Okay. This is called metric MDS. You could do it, of course, still with linear as well. That's fine. And one thing we talked about last time was, why do we even need something nonlinear? So the reason for that is some data cannot be, unraveled or cannot be like unfolded just using linear stuff. An example is this. And I'll try to show you some nice applets. Let me see. Where you see this nonlinear stuff doing why this goes to Bing. Yeah, there you go. And I will also open one more. Give me just a sec. Where is the link to the other thing they got? Come on. Okay. Somehow I couldn't find the link which is on this web page, but this is good enough. So this we will talk about what is this TSNE or UMAP. And here you could see immediately what they do to your data with different parameters. Yeah. For example, this is your NUT. And there was A1 where you get to train the model on the spot. Yeah, right here. So you go and you say, okay. You see it's kind of able to distinguish between the colors. But what goes in here is very nonlinear. And that's the type of stuff we will talk about today. I'll get back to this applet later. So the point is, if you have a task which cannot be done with just linear dimensionality reduction, those tasks do exist, you may want to do something nonlinear. Okay, so first idea we talked about is this k nearest neighbor graph. So you pick your data and you pick a k you like, then you draw the k nearest neighbor graph, and then that gives you a notion of a distance. To go from this dot to that dot, you have to go through the graph and find the shortest path. And we could compute those shortest paths efficiently. And then this becomes whatever the manifold I'm trying to fit, okay? Using this distance, you just do your distance multi-dimensional scaling, and you try to fit a manifold to your data. That's the earliest kind of manifold learning application. Then we started talking about kernel methods last time. So what's a kernel method? So we so far used, when your data is given by this matrix X, we either do X transpose or X transpose X. You end up taking dot product of data vectors and create a covariance matrix, right? So what we will do is we will allow ourselves not necessarily just use a dot product, but any function that will take two of your input data and spit out a number. What do we want from that function to satisfy? So a priori, you don't have to assume anything, but to make things work out, you want it to be positive semi-definite. What does it mean? When I put all those data points one by one and create a matrix of the outputs, if I have n data points, it will be an n by n matrix. That matrix should be positive, meaning that all the eigenvalues should be 0 or bigger. Okay, that's what I want. Because in that case, there's a theorem which is 100 years old, more than 100 actually. I looked up, this is seemingly a person in UK, so probably called Mercer. It looked like a French last name, but the paper is still accessible online. Turns out they scanned the first few pages of this paper. If you just Google Mercer's theorem, you can find the paper this guy wrote more than 100 years ago on proceedings of Royal Society of London or something like that. Okay. So what does it say? It says the following. If you got a kernel that is positive, and then you define a transformation based on that kernel, take any function. I'm writing one variable version, multivariate is almost the same. Take a function and then put the kernel on top and average over, integrate. Now you'll get a new function. And then this operation looks at your function space and it decomposes to eigenvalues, eigenvectors, eigenfunctions, okay? And the theorem says those eigenfunctions actually give you an embedding. What does that mean? So behind the kernel, secretly, it's actually taking your data, embedding it to somewhere, and you're doing linear afterwards, okay? And you don't have to compute this embedding. This could be very wild. You'll still be able to compute just with this kernel K. However, knowing that this exists is going to be helpful, okay? So that's why we want to use Mercer kernels, which means when you put that kernel, when you do that matrix by all the outputs kernel produces, that's got to be a non-negative matrix. That's all we want, okay? Because then we know this is actually an embedding, even though we don't see it. Okay, very good. So here are some of such kernels. This is apparently called automatic relevancy deduction. So what does it do? You take a matrix, diagonal, you put some numbers here, and you put inverse of it on top, right there. So if a diagonal has a big number, say it has got 1 million, the inverse will be 1 over 1 million. That means that corresponding feature starts getting ignored, more or less, okay? So the bigger number you see here, that feature is getting ignored. And you try to fit this to your data. That's why they call it automatic relevancy detection. So let me show you some pictures of this. So for example, the first one has L1, L2, 1. They're equally contributing. The second one, L2, 5. So the second dimension is more or less ignored. It's just going off first dimension. And that's why you see like a one-dimensional picture, more or less, okay? So these are just a whole bunch of kernels you could create, okay? This is one. You could, of course, use Gaussian. You could use this linear dot product. Yeah, there's a whole bunch of kernels you could use. And this gives you a lot of flexibility. Okay, so what are we going to do with this? So here's another kernel called radial basis function, I think RBF. Sounds like notorious RBG. Not that. All right, so this is another thing you would end up seeing a lot. And another thing you would end up seeing a lot is Gaussian processes. What does it mean? At every data point, you're imagining the embedding is some Gaussian vector. But let me get to the point that I'm more excited about. So you can use these kernels to make your PCA much stronger and much more capable. So how do we do that? So in the PCA, what we were doing, we were taking our data, do this covariance matrix, looking at these eigenvectors, picking up the top D1s, project there. That's what PCA was doing, right? So now we will replace the covariance matrix with the matrix given by the kernel. And we'll more or less do the same trickery afterwards, okay? But there is a difference. If you have, let's go slow, suppose I got, and this difference is important. Let's say I got a whole bunch of data points, x1, x2, xn, capital N, they are living in Rn. And we stack them up as a data matrix. We would usually go do XX transpose for covariance descent N by N matrix, right? But when you're doing kernel, you're going to put an xi and an xj. And they're going to get it out of the kernel. How many choices you got? N, capital N times capital N. So the kernel matrix is much bigger than the covariance matrix, okay? So this means computationally this is going to be much more heavy. I'm going to try to compute some eigenvectors of this gigantic matrix and project down in that direction. However, this also means you have a much stronger model in your hand. That's basically kernel PCA. Pick a kernel, look at the eigenvectors of the kernel matrix, do that PCA by projecting down on those eigenvectors. So how does it connect with this embedding that we know exists in the backend, even though we don't see it? Mercer's theorem was saying, if I got such a kernel, there's an embedding in the back. Let me try to walk you through that. So in the PCA, we have this covariance matrix, and we are looking at eigenvalues. What does that mean? Lambda times the vector is matrix times the vector, right? And if you write down this matrix XX transpose, C times V can be also written this way. You're literally taking dot product of your vector with all your data points, and you multiply that number with your data points, and you're averaging over, okay? And you want that CV to be equal to lambda V, right? And now multiply left and right with any data point X, you get something like this. X times your vector should be this sum. That's what you're solving when you're doing PCA. We'll do the same with this kernel. So in the kernel world, we know there's secretly an embedding, even though we don't know it, that it is there, right? And then I'm still trying to find the eigenvectors. And suppose your vector V is decomposed into those eigenvectors this way. Sorry, decomposed into those embedding vectors this way. Then you write down, you end up solving again a very similar equation. And the point is, you don't need to compute this embedding to be able to compute the solution. Why? If you look at it here, you're just taking dot products of vectors. You will end up taking dot products after the embedding. And we know that dot product is exactly what the kernel was giving. So even without computing the embedding, which could be huge, you're able to compute kernel PCA. Okay. And that's all there is to kernel PCA. There is some caveats. I will tell you about it now. But overall, this is the idea. So intuitively, you can think about it as follows. In the PCA, we were trying to project down on a linear space, which is the best fit. Here, we are kind of projecting down on that curvy stuff given by the kernel. Or you can also think about it as kernels secretly embedding them somewhere, maybe a gigantic space. And there I'm doing the PCA with a lot more features. You can think about it that way. All right. So far, the discussion assumes the data is centered after the embedding. That's not necessarily the case, but there are tricks to fix it. I don't think we really need to go through all details of this, but basically, even when it is not centered, by something called double centering trick, you get a good approximation to your computations. Okay. If you're interested in details, I'll put the reference on Canvas. But the main question here is like the embedding running in the backend, even though we don't see it, one way or another, it will show up in your computational complexity. You have this gigantic kernel matrix, you're trying to compute its eigenvectors. One way or another, you will see the effects. Okay. So like ideally, you don't want that embedding to be very wild. So people, after experimenting with this idea and sometimes things going crazy, they started inventing, turns out, techniques to have mild kernels, more or less, which still does a good job. Okay, so one such technique is apparently called maximum variance unfolding. What is that? This is what is your data after embedding. Okay, and this is the variance. You literally take that product to your data with itself, norm squared. You sum it up. Okay, you're trying to maximize the variance subject to what? After your embedding, distances will be preserved with respect to a graph. What is that graph? You get to pick it. Usually you would do k nearest neighbor graph. So you take your data, you fit some k nearest neighbor, and say you care about 6 neighbors for every data point. Okay, and then you want that distances with the neighbors that are important to be preserved. That's the only constraint you're putting. The rest, you say maximize the variance as much as you want. Why? You need to think about it as if like really I'm trying to unfold and make that complicated graph like flat. I'm trying to give as much as variance as possible. Spread it out as much as you can so that it doesn't become like a crazy embedding. That's the idea behind this. So, okay, nice, intuitively good, but can you actually do this? Turns out, yes, this is a convex optimization scheme, at least computing this on your kernel matrices. So let me be more precise. So the variance there will correspond to trace of your kernel. Why? What was your kernel? Entry II will be that product after embedding with itself, right? And this is the same thing as ZI. So this is the diagonal entries, and summation of all those diagonals is the trace, and that's literally the variance. So you're trying to maximize the trace of your kernel, and you want your kernel to be a positive matrix, and you want it to respect nearest neighbor distances, okay? Finding such a matrix is something called a semi-definite program. It's a type of a convex program. It is the next level after linear programming. The most simple and the thing we can run at scale is linear programming. The one next up is this guy called semi-definite programming. There are companies which give you solvers for this. I think the Mossack was like a Danish company. I think they were dominating this market for a while. For linear programming, there's a lot, like there's Groby, there's a whole bunch of companies that sell linear programming solvers. For this, there are companies, but it never really took off as like linear programming. So those companies are not so rich. They're making some money, but not so much money. All right. The point is we can do this. So you compute that kernel, and then you run your PCA with that. Okay. Yes, go ahead. So this is a general discussion, not only linear programming, overall techniques that came out of operations research. So, right, operations research as a field started out around Second World War and so to do resource allocation, logistics, optimizing operations. And initially, it was a big deal because people were running a linear programming solver on their company's resource allocation, just making a whole bunch of more money by better optimization. Nowadays, somehow, with deep learning becoming so successful on so many things, people started forgetting about operations research. It is researching under the name of decision scientists these days. So the people who are called decision scientists are actually people who understand a little bit of operations research and maybe can talk to ML people. Okay. And the point is that when you do stuff with linear programming, semi-definite programming, you know your model, you know you solve it correct. You kind of know what's going on. So that's the difference from ML. In ML, most of the time we are fitting a model. It is good 80%, not so good in 20%, you know, whatever it may be. But if you're trying to make like a business decision, maybe you want a little more guarantees than that. So that will be my short answer. That's about, yeah, let me say that and move on. Okay, so this is that. And in the textbook, I was looking at it and it's wrong. This is the correct version. I emailed Kevin Murphy. He accepted his mistake. He'll fix it. That's what he told me. Okay, so this is the correct version. Okay, so this is maximum variance unfolding to have a reasonable kernel. Any questions about this so far? We will get back to kernels in a little more simple form when we talk about classical machine learning after we are done with dimensionality reduction. Overall, I hope it's looking reasonable. You're replacing that dot product, essentially, that you saw in covariance matrix with this kernel. But kernel allows you to be more flexible. Suppose your data is a string, your data is a graph. You know, dot product, you only do it when you got vectors already. Kernel, you could do it with whatever you want. Okay. All right. So next dimensionality reduction technique in line is called local linear embedding. What does that mean? It means I am trying to use a whole bunch of linear regression together, essentially. Okay. That's what it means. So locally, it will be linear, globally not. So more precisely, you again decide on a neighborhood, maybe by a k nearest neighbor graph or whatever your process of deciding neighborhoods is. If two data points are not in their neighborhood, you just put the weight to be 0. You don't care about it, okay? But if it is in the neighborhood, you'll get a weight, and then the summation of weights of your every single data point should be 1. You're literally putting weights on the neighbors, okay? And then you're trying to minimize the loss. You're trying to see your data point as average of its neighbors. What was that? You're like the average of your best 3 friends or something. That's kind of what this is trying to do, okay? Instead of treating every data point as an individual, it says, okay, I'm gonna zoom out and make it look like average of the neighborhood and trying to do the best fit of such, okay? That's local linear embedding. You know, you see the power of this after you play with it a while. So there's tricks to get it to work, etc. So I never spent too much time with this, but if you have some experience, it becomes a powerful tool. Okay, all right. So the next thing you will hear a lot is called stochastic neighborhood embedding. And this is mostly used when you have to do a visualization. So you're in a meeting, you have to do 2D or 3D visualization of your data, okay? So like a lot of dimensionality reduction techniques will not bring your million feature data to 2 dimensions. Okay. So this is what you use in those kind of situations. This is invented by this famous guy, Georg Hinton, sometimes called Godfather of AI. And I think maybe Ilya Sutskever, I forgot the rest of the authors. So what do? They're saying, I'm gonna use Gaussians, all right, to talk about an embedding, okay? And then I'll try to see like a graph where the weight of the edge between data point I and data point J will be given by the Gaussian. I take the Gaussian density between those, and I sum up all the Gaussian densities with this data point, and that's my weight of this vector edge, okay? And what do? You want to preserve those weights, basically. That's how this thing is cooked up. You reduce it to dimension 2 or 3 in a nonlinear way, And after that, you would like the new weight distribution to look like the one before. Okay. So let me go back to. So this is something like TSNE. There is also a very nice exposition on TSNE. I will put it on Canvas. This is how it looks. For example, this is what? Probably fashion data. Yeah. And you're pushing down 784 dimensional data into just 3 dimensions. Okay. And TSNE is this thing on the right. And you see it's kind of figuring out the clusters, like trousers, bags, sneakers. They're not too far from each other. Yeah. But there is a lot that goes into making this thing work. So one problem with this is it's too sensitive in this form to a little bit of perturbations and outliers. So if a data point is way out, it starts dominating everything right here. It's going to have a huge difference from everyone, and then you exponentiate it. It's like, it's okay. So it's very sensitive to outliers. And that's why it got updated afterwards. Okay, so this is using Gaussian. And if you remember early on in the semester when we were discussing basic probability, something that is similar to Gaussian but a lot less sensitive is called student t distribution. Okay, I'll remind you what that is again, or at least give you pictures. So this is how it is defined, not so important. The main point is student t distribution is a lot less sensitive to outliers. So what you do, you take the same SNE. Instead of Gaussian, you plug in student t distribution. Then it gets called TSNE. Okay. And that's a very common dimensional reduction technique used all over the place. But there are like parameters that goes into this. One is you again start thinking of a neighborhood, and then you can mess with the distance metric that is involved. So it takes some experimentation to make this actually work. But when it works, it just gives you a 2D, 3D visualization of a very complicated data, which is very useful. Yeah. Okay, so this is TSNE. And the main and as I said, it takes some experimentation to make this thing work. So that's why people invented this more recent thing called UMAP. Okay. It's called what? Uniform Manifold Approximation Projection, something like that. And what does UMAP do? It says, okay, TSNE is nice, but it's so sensitive. You have to do a lot of work to get it to work. We want to design something more robust. So what do they do? If you have 2 hyperparameters to play with in UMAP. First hyperparameter is you swell your data points. Okay. You give it like a neighborhood, that's extent. Then you also pick how many nearest neighbors you care about. And the nearest neighbors are picked among the ones where their bubbles intersect each other. Where they are in their influence zone, among the data points in your influence zone, you pick the closest 5, 10, whichever one you pick. Let's say, let me increase this. You see, it's picking out more and more neighbors. Or if I swell more, it's going to start getting more connected. Okay. So after this is done, you get a graph of this, and you build your stuff based off of that graph. Okay. So instead of just nearest neighbor, you allow like a trade-off between how influential is your data versus how many nearest neighbors you like to care. You can play with both hyperparameters. The intuition behind this is coming from a field called algebraic topology. So in brief, algebraic topology tries to think about everything like a whole bunch of simplices. Okay. So, if you have like 4 data points, let's say, I don't know. Okay. So think about like an triangle pyramid, like 1, 2, 3, 4. That's a simplex. Okay. So in any dimension, there will be simplices. In 2D, what's a simplex? Just 3 points, a triangle. So algebraic topology tries to look at the shape and decompose it into those simplices. Okay. So this is trying to look at the whole data as a decomposition of a whole bunch of simplices. You can think about it like triangulation. And that's where the intuition is coming from. I like this stuff, but I'm not going to talk about it now due to time reasons. If anybody wants to learn more geometry, we can talk anytime. And UMAP is currently kind of experimentally verified to be more robust than TSNE. And there is a lot of growing packages on UMAP. So eventually, I'm guessing they'll be capable of doing the hyperparameter optimization for you. You'll just call UMAP and it will do the thing for you. That's what they're trying to do. Okay. So I'll put this on our canvas. You can play and see, and I would recommend you to do so. Yes. Okay. Let me get back to our discussion. Let me see if I have anything else I want to say. Oh yeah, how did I forget this? So any questions so far? I gave you kind of a survey of manifold learning as a field and the most prominent techniques. This is chapter 20 in our textbook. Just keep this in mind whenever you need to do dimensionality reduction. If linear is not cutting it, you might try nonlinear. Okay. So when I was talking about kernels, I wanted to say a little more about them, then I forgot. Let me do it right now because we are going to use kernels in what's coming. Now we will start classical machine learning today and next lecture. The things people used to do before deep learning took over the world. So kernels will play an important role. So let me say a few more things about kernels. So kernels are kind of a world on their own. You can add them, you can multiply them, you can exponentiate them. You can create new kernels from old ones. How does it look? So here it's a plot of adding and multiplying. Yeah. Addition is more or less like convolution that we have seen before. If you keep adding, you're going to get smoother and smoother. Multiplication is a little more crazy. It is convolution in log space, essentially. You can think about it that way. That's something you could do with kernels to fit them better. And that's not the only thing you could do. You could take a constant, multiply your kernel with that. You could put a function on top of your kernel. You could put it inside a polynomial. You could exponentiate it. Or you could do a matrix change, etc. Okay. So this is all possible. It gives you like a lot of flexibility. Okay. Very good. That's all I wanted to say about kernels. Let me go to the classical machine learning discussion. So one thing is like, we will talk about this soon. You can use kernels to also create something like a probability distribution on your data. That's called kernel density estimation. I will talk about it soon. That's a place, if you can afford it, if your data is not gigantic, or if you want to do an experiment with small, that's where I would do kernels. Where else I have done kernels? There's something I'm going to talk about called neighborhood component analysis. There also. Then that's about it, I would say, for me, but it's just my limited personal experience. These tools have been around for a long time. And knowing them also helps you. For example, in the transformers paper, the paper that introduced transformers, attention is all you need. the way they think about attention is actually they're thinking about like a kernel. If you just read the paper, you will see what I mean after you saw kernels today. They are imitating, I think it was called, what is it? Watson Narayana kernel from 60s, essentially, something like that. Yeah, that is true also. Very, very good observation. People use this word kernel for so many things, it gets confusing. I agree. Yeah, that is true. Yes. Okay, let's get back to, okay, now I'll tell you about sometimes what's called non-parametric models. So what's a non-parametric model? When we do neural nets, we have weights or some parameterization of the function we are building, but that doesn't have to be the case in your model. These are sometimes also called example-based models. Yeah. So the most classic one is K nearest neighbor classifier. What's that? You pick a K you like, how many neighbors you will care about, and you have a classification task, and you look at those neighbors, and then you assign probabilities of the classes with respect to the neighbors. Neighbors are labeled data. You got your labeled data, you have a new data point coming in, and among those labeled data, you look at the closest 5 ones, okay? And all of them are belonging to class 10. Then you say, this guy is probably class 10. 3 of them is belonging to some class, 2 of them other. Then you say, okay, 3 out of a 5 probability here, 2 out of a 5 probability there, okay? And here is a picture of 5 nearest neighbor and 1 nearest neighbor. There is something counterintuitive here. Which one is the most complex model among this case? 100 neighbors, is it more complex or 1 neighbor more complex? If you say 1, pretty cool. You know, when I was first learning about this, I was like, more neighbors looks more complex. And I realized what it is trying to do is like, it's trying to put a kernel, essentially. When you say 1 nearest neighbor, it's just putting a kernel on top of every single data. Okay. When you say 100, it's like averaging over 100, so you're putting less kernels. So your model is less complex. So when you're fitting KNN, you need to start from a bigger K, make your way of like cutting it half to avoid overfitting. If you go with 1 directly, you might just overfit. Yeah. You guys are smarter than I was when I was learning this, turns out. So I was like, 1 should be the easiest, but turns out it's the most complex one. Still, nobody gave me a hint, that's right. All right, rough learning curve, whatever. Okay, so now, again, some more plots. As you see, decision boundaries gets more and more complicated as K gets smaller. So K equals 5 is picture C, K equals 2 is picture B, K equals 1 is picture A. This is super data intensive. As you see, you know, it's using all labeled data at once, essentially. It's like something that could kill your memory very easily, unless the implementation is super careful. But if you're able to pull this off, it usually gives very good results. If you have not so gigantic data, this could be the first thing you start from. Okay? And people develop later a lot of tricks to get rid of data points that does not change the decision boundaries so much. You know, let's say this data is important for this boundary, but maybe these guys are not so influential. So people come up with a whole bunch of tricks on trying to get rid of the data points that are not important for decision boundaries, try to do the memory allocation cleverly so that this runs faster. Even the off-the-shelf scikit-learn implementation is not bad, basically, at this point. It's been around for quite a long time. All right, so this is our K nearest neighbor classifier. And in K equals 1 case, it has a name called Voronoi diagrams. So this existed in other fields, invented for other purposes. Okay. All right. Okay. Now, here's an observation. If you have this K nearest neighbor classifier type mindset, you have a closed world. You have data points labeled and fixed. You're trying to classify everything based off of those. That's it. Okay. But maybe you have a new data which doesn't look like any of them, right? Suppose you're trying to classify faces, or you're trying to classify pictures, art pictures from classics. You have seen some, but not all. So in that case, you might try to come up with a model which has a code says out of distribution. So your data comes in, it tries to do something like KNN, but then you have to come up with procedures to decide if it is not looking like anything you have seen before. Then you call it a new data point and you put it inside your model. You update your model. This is sometimes called open world learning, sometimes called lifelong learning, sometimes called incremental learning. People have come up with a whole bunch of different names for this. But the main point is like you allow your model to get updated, even though it is not parametric. You have to have a way to decide if something is out of your distribution. Okay, that's about it. So far, so good. Any questions? Yeah, go ahead. Yeah, sometimes maybe continual learning might be one of the names that is used too. Yeah. But sometimes continuous learning is used more for RL type environments, so you need to look at the context. Sometimes people mean you can keep learning. That's not the case for every training environment. You need to be careful and check. Okay. Now, so far I did not discuss at all how do I measure distances between neighbors. We assumed we are given a distance. We assume probably our standard Euclidean. That's how we go, right? But this doesn't have to be the case, especially if your data is a graph, string, document. Maybe you have to come up with a different metric than just like measuring Euclidean. And this is called metric learning. It's a field on its own. And unfortunately, deep metric learning has been populated by so many papers that claims more than they deliver. So if you're looking at a deep metric learning paper, try to be very careful. I don't know why this field became this way, but this is what it is currently. I'm going to start from classic metric learning techniques. Also touch base on deep metric learning. So the main point is you're trying to learn a metric that represents the structure of your data, whatever data you're working on. It does the job better than your standard Euclidean, okay? So one old thing that is called neighborhood component analysis. The way I wrote it here, or I took it from the book, is the linear one, but it doesn't have to be linear, okay? So W here takes your data, multiplies it with the matrix. But here, instead of W, you could have a neural net doing something to your data as well. Okay. So what do? You take, this should be labeled data. And suppose you're doing a classification task. Okay. And you're trying to come up with a way to change your metric or transform your data so that your classification task is going to get easier. Or you can imagine also say clustering task or community detection task, okay? You have some labels, and the label tells you which data is relevant to which. And you're trying to train on it so that when you see new data, you're gonna be able to capture that clusters or communities much quicker, okay? So what do? This Pij is like a weight. Again, it looks very similar to this SNE weights, if you remember. In SNE, it was also like exactly this, more or less, because it's invented by exact same people. That's why you see the same ideas. But this was before TSNE, I guess. I have to check. Okay, so what do? You put this weights, that's about like how close is your data to each other. And then for every single data point xi, you create something called pi. You go through the weights for the data points j that are in the same class with your I with respect to your label. Then you sum up all these, and you're trying to maximize the sum or minimize minus the sum. That's your loss function. You could do this linear, non-linear, and this is very useful. I don't know why people started forgetting about this. we were trying to use this on a project with Farhan this semester for some astrophysics problems. So astrophysicists are interested in open clusters. So what is that? It's like some stars are born and they kind of get into gravitational lock and they go together in millions of years. And so after some point they dissolve and then new clusters merge. And they want to keep track of those clusters, but they don't have apparently good algorithms to do this. And they started talking to me last year, and eventually I said, okay, we can work on this. So what we are trying to do is we are trying to learn a metric, and which will make this open cluster stars looking closer to each other and kind of sticking them out from the field of other stars. Yeah. And we realized this neighborhood component analysis is pretty useful, but the implementations weren't so great. So apparently a PhD student in Berkeley wrote a PyTorch implementation of this like a few years ago. And we had to kind of update it. So I guess by next year, we can also release our own NCA implementation and you guys can use it. Okay? And you could do linear, nonlinear, whatever you want. Just don't forget to regularize your nonlinear stuff. So Farhan forgot to regularize and we ended up having like a monster neural net. And now we are trying to tame the monster. That's what's going on currently. Anyway, so we'll have a decent implementation soon that you can use. Okay. Now, this is one way of doing this. There are variants of this. You don't have to do, for example, Gaussian. You can just do norm. Or you can do some other loss functions. They have different names, but it's all the same idea. Look. Here is another idea that you would see in this deep metric learning literature a lot. So it's a little mathy. Bear with me. I'll tell you what this is. Basically, the idea is this. You can do whatever neural net architecture you like for learning a metric, but you need to end up needing a loss function for your train. What kind of loss function makes sense if you're trying to learn a metric that represents the structure of your data well and it's suited for your application? People started thinking about this, and then first thing that people came out is called constructive loss, sometimes also called twin loss. I'll tell you why in a sec. What does it do? If your labels of these two data points are different, which means they are from different class, you put them here. And if they are the same, you put them there. And this is your loss function. Okay. This delivers some results. However, since you completely decoupled the ones in the same class with the ones they are not, sometimes you get a lot of nonsense out of it as well. So that's why people said, okay, let's not decouple that much. They come up with this thing called triplet loss. What is it? You take triples, xi, xi minus, xi plus, and you do xi plus is somebody in the same class. Xi minus is somebody in a different class. You're trying to differentiate a lot. You take in different and same class at the same time. On top, they were completely decoupled. Here, they're trying to use the information together. Yeah. And then, okay, of course, when you go from 2 to 3, no one stops you to do more. People also did that. So it's called N loss. You can use also not only just 3 N data points, because triplets turns out to have a lot of variance. Okay. And that's like probably, this field is, as I said, big. And what I'm showing you is a little old. It's not like last 2 years, because it started becoming hard to navigate in the last few years. That's why. So here is illustrations of these ideas. So the first one, this contrastive loss, is also called Siamese network. I guess it goes after Siamese twins. Okay. People are creative with names. And what are you trying to do? You're using the same neural net to attack similar and dissimilar images at the same time. You're trying to train two same architecture neural nets with the loss function that you got. That's why it's called Siamese structure. And the triple one is here. It's a little more symmetric and nice, and also gives less variance, turns out. You got three things in. This time you're not decoupling similar and dissimilar completely, you're putting the information together. That's how the structure looks like. All right. But there's a lot of new developments in this field. Some of them are cool, some of them are not. I did not want to get into delineating all that stuff. So this is more established and experimentally verified stuff that I'm showing you. Okay. Okay, so far so good. Any questions? So main punchline from this is, instead of defaulting on a Euclidean metric, think about if it is a good idea to learn the metric a little bit from your data first, then do whatever model you're going to do afterwards. This could be thought about like a modular. That's, for example, what we are doing with this astrophysics project. So NCA is just the first step. After we learn the metric that sticks out the clusters of stars somewhat, we will do some other embedding stuff to actually figure out that cluster. This could be like a modular first step. Don't default on Euclidean. Learn a metric first, if you like. Then whatever model you're going to do based off of that metric, you can do it as you would do otherwise. Okay. All right, very good. Now, kernel density estimators. This is essentially a generative version of this KNN classifier we started off with. You're trying to put a kernel on data points. And here, kernel just takes one data instead of two. And Adam is right, this is again like when they say kernel, do they mean two data, one data? Yeah, this is also called kernel, but not too far from the kernel we have seen. The most classic one is Gaussian. You would usually introduce something called bandwidth as a hyperparameter. And you could put it in your Gaussian. Or you could put it in this, what's called RBF, radial basis function. And then it will look like what is right there. And you're going to mess with it to make it fit the best. And here is like an illustration of some classically used kernels. What's the difference? You put this kernel in, and you do your classifier based off of this. Then if somebody asks you to generate a sample from your data or a sample from such and such class in your data, since you put a probability distribution, you can generate. It's more or less trying to do KNN, but I have a probability distribution, so I can sample. That's more or less the idea of this stuff. Sometimes you don't have to sample. Sometimes you just need to fit a distribution to your data. And this can do that for you as well. Okay, so here is what I just said in more detail. Pick a K, your K nearest neighbor. Thicken every point until it's got K neighbors. Then look at the region that you thickened your point until it's got K neighbors in that region. And that's called the area or volume of that region is what's this Vx. Then your classifier goes like this. It looks at the number of points that is from a certain class in the neighborhood. divides it with the total number of points from that class in your data, labeled data, and normalize with the volume corresponding to your particular data point X. And that will be the probability distribution this guy spits out. Now, if you combine this classifier you created with kind of a uniform prior, what's the uniform prior? Being from this class has probability of number of those class elements divided by all my data points. You do the math, this ends up giving you exactly what we were doing in K nearest neighbor as a probability distribution. So the difference here is, now I got my probability distribution. If somebody tells me, can you give me a sample from class 5? I can use my probability distribution to sample. Otherwise, it's more or less doing this K nearest neighbor. Okay. All right. So this is KNN classifier. Any questions about this thus far? Okay. Now I'm going to talk about something called large margin classifier. This is also known as support vector machine. Probably you guys heard this term somewhere, support vector machine. Have you heard of this before? SVM. Oh yeah. So SVM is a general term. I'll try to tell you what that is. But the main idea, I think this picture is giving like the main idea. Suppose you're trying to classify these data points. Okay. Would you like this one or that one? Here, if you would have a little error, you will miss that data point being in the correct class. Here, you have wiggling room for error. Okay. So basically what you're trying to do is like, you're looking at the margin from decision boundary. And you're trying to make that margin big so that if you got some errors, you don't mess up. That's called large margin classifier. Okay. So, and there are different ways of doing large margin classifiers. And that gives you the support vector machine family. So let me try to walk you through it. So here's another picture that I like. So now what the picture is saying, suppose we are doing linear for the moment. You don't have to do linear. Let's say we are doing linear, okay? The decision boundary is given by some linear stuff. Suppose it's literally like this vector W multiplied with your vector X equal to a number, v.x equals to 5, whatever. Let's say that is the decision. Now, how do I talk about the distance of my data point to the decision boundary? Turns out you just need to think about what will be the projection of your data point on the boundary and look at the orthogonal vector from there, okay? To write it in a more mathy way, what you do is like you take your data point. This is the projection. This is some number. This is the direction going towards your data point from the projection. And what you want that number to be as big as possible. That number is your margin from the boundary. If this is 0, you're literally on the boundary. Okay. So let me show the picture again. So that R is like the direction of the vector multiplied with a number R. The bigger margin, the bigger the R. Okay. Okay. Now, so what does that mean? So your function is that weight on your data point with some bias here. And then you decompose as it was written there. And you go through. And since this projection is literally on the decision boundary, this has got to be 0. So you end up getting your fx to be this R multiplied with the magnitude of that weight vector. So literally R ends up being the function divided by magnitude of the weight vector. And that's what you're trying to maximize. In other words, you are trying to maximize this quantity. Okay. But this looks a bit funny. I don't know how to deal with this. So one thing you notice is like, since this weight is in the function, and then the function gets divided by the norm of the weight, scaling the weight vector doesn't change anything in this discussion. You take the same vector, multiply it with 5, this is going to remain the same. Basically, scaling the vector does not change your distance to decision boundary, right? It makes sense. So what you do is like you scale your v to make this part always bigger than or equal to 1. And this way, you can ignore this, only deal with that. And when you do that, it looks like this. All that stuff is bigger than 1. Instead of maximizing 1 over your thingy, you minimize the thing itself. This is much more mild to deal with. Okay, and that's how you would train a linear large margin classifier. And the reason this is called support vector machine in general is when you have a data point, you don't expect it to be close to a whole bunch of decision boundaries. So I got my data here. Maybe it's talking to, say, 3 decision boundaries, but in total, I have 100 of them. So the 3 is kind of the support of that data point. It's the support vector. Okay. So overall, you don't want to use a lot of decision point boundaries at the same time. You want to keep it sparse, and that's going to be your support vector. Okay. The general version of this looks like this. Instead of weight dot with my vector, I could also do a kernel, as we learned about kernels. This would be a general support vector machine. You're going to try to cook it up so that you don't use so many of those kernels. A lot of these alpha i's, you want them to be 0. And the non-zero alpha i's are the support vector. Okay. So to put the analogy with the linear thing more precisely, instead of this weight right here, you're going to put the kernel right there. And instead of the average weight, you're going to do some kernel stuff. And as I was writing here, allowing yourself to use kernels allows you to be not so explicit. When you're doing dot products, you have to literally have vectors and dot products. You can create a kernel on strings, on graphs, whatever you like. You don't have to have like a precise vector embedded. Okay. And that's about this. Let me see if I have anything else. I think that's more or less good enough for this part of classical machine learning discussion. Thursday, I will talk about trees, decision trees, random forests, bagging, and boosting. Boosting is a technique to boost the capabilities of weak models. It's sometimes also called weak learner model. Funny enough, you have a lot of weak stuff, you combine them in a correct way, it gets much stronger, surprisingly stronger. That's boosting. Bagging is the previous idea of collecting stuff in the same bag. You know, instead of a tree, you get a forest. And that's about it. So I will talk about this trees, bagging, and boosting, and that's more or less all I wanted to say this semester. So, very good. And if we would have a lot more time, one should spend experimenting with something like XGBoost or CatBoost. I'll tell you what they are. But when you really learn its power when you use it. So that you have to do on your own. XGBoost is what people used to do before deep learning took over everything. Quite often, people who know XGBoost well is still what they would do at the beginning before using deep learning. It's very powerful, and it's a little more interpretable than deep learning. So it's not directly interpretable, but not too bad. It has some decision tree flavor to it. You know, when you say decision tree, it's easy to understand. It's like taking my variable, asking a question. Is blah feature bigger than such or no? Yes, no. You know, you see literally the decision tree. It's pretty interpretable. When you start doing random forests of decision trees, it starts getting less interpretable, but still not too bad. There are some techniques to come up with interpretation of random forests. And this XGBoost is not too far off. Okay. It becomes a lot less interpretable compared to a very simple decision tree, but still doesn't feel as black box as deep learning. Okay. All right. I think that's good enough. I don't want to take more time today. I hope you forgive me for finishing 7 minutes earlier.